the reaction that made control an illusion. At first, it felt like mastery, a reaction so well understood it seemed fully under human command. Variables measured, outcomes predicted, control appeared absolute. In laboratories and production facilities alike, this reaction became a symbol of confidence. It behaved exactly as theory promised. Adjust the inputs, monitor conditions, and the outcome followed reliably. For scientists and engineers trained to trust equations, this was chemistry at its most reassuring. The reaction did not surprise. It complied. For decades, chemistry promised certainty. If you knew the conditions, you knew the result. This belief shaped industries, medicine, and technology. Entire systems were designed around the idea that reactions could be mastered once their parameters were mapped. Control became the central promise of chemical science. And for a time, that promise seemed fulfilled. To understand why this reaction matters today, we need to look at how control is defined. In chemistry, control means predictability under fixed conditions. Hold temperature steady, maintain purity, apply the correct timing. In isolation, these assumptions hold, but the real world rarely offers fixed conditions for long. Outside the lab, variables multiply and refuse to stay still. At first, the reaction performed flawlessly. It delivered consistent results. It scaled smoothly from small tests to industrial use. It integrated easily into complex systems without demanding radical redesign. Each success reinforced confidence. Chemistry felt solved, not just understood, but conquered. But scale introduces variables no equation fully captures. Temperature fluctuates across environments. Materials vary subtly from batch to batch. Human behavior interferes with ideal procedures. The reaction continued obeying chemical law, but the environment stopped obeying assumptions. This is where the illusion began. Control existed only as long as conditions stayed narrow. As long as purity was perfect, timing exact, and surroundings predictable. Once the reaction escaped those boundaries, predictability softened. Chemistry was still correct. Control was not. The story begins here, with a reaction that taught humanity a humbling lesson. Mastery over chemistry does not equal mastery over complexity. As reliance on a reaction grew, systems were built assuming control was permanent. Safety margins shrank to increase efficiency. Oversight relaxed as confidence replaced caution. Chemistry had proven itself reliable, so everything else adjusted around that belief. Redundancy felt unnecessary. Flexibility felt inefficient. At first, nothing went wrong. The reaction adapted to new contexts without obvious failure. Production increased. Costs fell. Efficiency improved. Confidence deepened. Control felt earned, validated by results rather than questioned by theory. But chemistry does not guarantee isolation. Reactions interact with their surroundings, and surroundings change continuously. Minor fluctuations began altering outcomes in subtle ways. Outputs drifted slightly. Reaction timing shifted. Side reactions appeared where none were expected. Nothing catastrophic, just enough to be noticed. This is where early tension emerged. Engineers responded by tightening controls. More sensors were installed. Adjustments became faster and more frequent. The system grew more complex, not more stable. Each new layer of control introduced additional dependencies and new points of failure. What made this dangerous was invisibility. The reaction still worked most of the time. Failures were rare, but when they occurred, they were disproportionate. Chemistry was no longer failing gently. It was amplifying small deviations into significant consequences. Scientists studying these events began to see a pattern. The reaction itself had not become unpredictable. The system surrounding it had. Control depended on conditions that could not be guaranteed at scale, no matter how carefully they were specified on paper. The illusion persisted because success remained common. Most runs succeeded. Most outputs met expectations. But chemistry was quietly revealing a deeper truth. Control is fragile when it relies on perfect circumstances. The conflict reached its peak when rare failures stopped appearing random. What once seemed like isolated anomalies began forming patterns. Different locations, different operators, different equipment, The same chemical outcome, the same failure modes. Investigations revealed a shared cause. The reaction was sensitive to variables no one had prioritized. Trace impurities present at negligible levels. Micro fluctuations in temperature or pressure. Timing differences too small to register in controlled tests. Chemistry was obeying its laws perfectly. Human expectations were not. This buildup carried emotional weight because the promise of control had shaped everything built on top of it. Infrastructure assumed stability. Safety protocols assumed predictability. When those assumptions cracked, consequences escalated rapidly. Systems designed for precision lacked tolerance for deviation. Attempt to tighten control only pushed systems closer to their limits. Tolerances narrowed. Corrections became more aggressive. Margins disappeared. Chemistry responded by becoming less forgiving, not more manageable. Precision increased brittleness. This was the moment of realization. Control had never been absolute. It had been conditional. The reaction worked beautifully inside boundaries that reality could not guarantee. Outside those boundaries, the reaction still worked, but not in ways humans expected. The illusion collapsed not because chemistry failed, but because complexity exposed a gap between equations and environments. Mastery over reactions did not translate into mastery over the systems they inhabited. What felt like command was revealed as negotiation. And chemistry, unlike humans, does not negotiate under pressure. The climax arrives with acceptance. Control was never the promise chemistry could truly offer. Understanding was. The reaction did exactly what chemistry allowed it to do. It followed physical law with precision. What failed was the assumption that precision equals dominance. Chemistry operates within systems that extend far beyond the lab bench. This insight reshaped how reactions are designed, not for perfect control, but for graceful failure, for tolerance instead of rigidity, for systems that bend before they break, rather than shatter when conditions drift. The resolution is already underway. Modern chemistry emphasizes robustness over optimization, diversity over singular pathways, designs that assume imperfection rather than deny it. Success is measured not by flawless performance, but by resilience under stress. This story teaches a humbling lesson. The more tightly we try to control chemistry, the more brittle our systems become. True mastery lies in working with uncertainty, not pretending it can be erased. Understanding this changes how progress itself is measured. Success is not a reaction that never fails, but one that fails safely when conditions shift. Chemistry did not take control away. It revealed that control was always an illusion, and in that revelation lies the path to wiser science.